Hi students, welcome back to geology. Today we are going to look at the crust in depth and what happens when it deforms. So why don't rocks just stay put and why are they dynamic and changing? So as you ponder this video or think about this concept, if you slowly squeeze a solid rock over millions of years, what do you think happens to it? Does it stay the same? Does it bend? Does it break? Why or why not? So first, let's take a look at crustal deformation. This is any kind of bending, twisting, or breaking of the Earth's crust, which are the rocks, right? So this can result from plate tectonic motion. So we've learned about plate tectonics so far. As things move and shift, stress is being applied to these rocks. And when these rocks deform in relation or in response to that stress, we call that strain. And not all rocks are going to accommodate the stress or experience the same strain. Some of them are going to bend, some are going to break. We might see shortening or stretching or thinning or shearing. It depends on the motion, the plate tectonic motion, and it depends on the strength of the rock. So there's some factors that we'll talk about that help determine what a rock's going to do when it experiences stress. Kind of like what you would do when you experience stress, right? Depending on your state, you might be like, okay, I got this. Or maybe you break down and cry because, oh my gosh, I can't handle this amount of stress. Well, rocks kind of do the same thing. It depends on their state. Okay, so the first thing is we need to look at what type of stress this is. Are we experiencing, or are the rocks experiencing, tensional stress by pulling apart? So like at divergent plate boundaries. Are they experiencing compression or pushing together like they would at a convergent plate boundary? Or are the rocks experiencing shear stress where things are just sliding past each other like at a transform plate boundary? Depending on what type of stress the rock is experiencing, we're going to see a different type of strain. So with tension, we oftentimes see stretching and thinning. So if you remember from divergent plate boundaries, as things are pulled apart, they get thinner and thinner in the middle. The crust gets thinner, and so you get stretching and thinning. With compression, when things are being pushed together, you get shortening. So things get shorter in this direction, in the horizontal, but they get thicker in the vertical. And so you can see in this image where things are being pushed together, things are also expanding up and down vertically. And then with shear, the resulting strain is often just tearing. So things are just being torn apart along that stress point. Okay, and we're not there yet, but I also have the associated fault type there for you. So with tensional stress, we're going to see normal faults. With compressional stress, we're going to see reverse faults. And with shear stress, we're going to see strike slip. And so these are the relationships between the type of stress, the plate boundary, the strain that's a result of that stress, and then the type of fault that we're going to see. Okay, and the next couple of videos will go over faults, but for now we're focusing on just understanding crustal deformation. So in geologic structures, we can identify the strain that they have created as a result of the stress they were associated with. So for example, in general, if there are fractures that don't show any offset, we call those joints. So the rocks tried to break a little bit, but there wasn't an actual offset to create a fault. There might be folds, which will be the next video that we talk about, where layers bent. So going from left to right is what we're looking at here. So upper left, right underneath strain is some joints where there's cracks in the rock. Right underneath that, we have a fold that forms kind of a V there. And then next, if the rocks cannot bend to accommodate that stress, they might actually fracture and create an offset where we call that a fault. So faults are fractures that show offset either horizontally or vertically. And so that's that middle image there. And then finally, at the crystalline level, we can also see something called foliation, which is a metamorphic fabric in which minerals align themselves parallel to each other, but they're perpendicular to the stress that they experienced. And when we get to metamorphic rocks, we'll go over that again, but just kind of keep that in the back of your mind, in your notes, as a type of strain in relation to stress. All right, so what decides what the rocks are going to do? So they experience the stress, and we know some of the strain that they're going to exhibit, the stretching, the shortening, the thickening, all of that stuff. But what decides whether they're going to fold or maybe they're going to break and fault? Okay, so that has to do with whether they are elastic, ductile, or brittle. Okay, so on the left-hand side here, we have stress and strain, and it kind of shows you what happens to each of them as more strain or more stress is applied. And then underneath that, we have a table that shows you what factor is going to give what strain response. So if temperature is really high, so we're like deep inside the earth maybe, so think about that pondering question, we're going to see something that's more ductile. Ductile changes shape permanently in rocks. So a metal bar was bent too far. Okay. Brittle is rocks lose their integrity, or they fail, or they fracture. And so we're going to see that with an increased strain rate. Okay, and then we're also going to see that with increased rock strength. So the stronger the rock is, the less elastic it will be, and it won't have any ductile deformation, which is the bending part, because it just cannot accommodate that, and it will break. Okay, so brittle is breaking, ductile is bending, and elasticity is when it changes shape temporarily. So if you move like a rubber band, it snaps back to its original size, right? You stretch it too long, of course, you start to change its size. But that would be ductile deformation that you're applying now, where the change is permanent. Okay, so temperature is really going to play a factor in the ability of rocks to change shape permanently, but not break. Okay, so that's the bending. So when we talk about faults and folds, ductile deformation creates folds, and brittle deformation creates faults. And there's also something called the yield point. The yield point is the point at which elastic deformation is no longer possible and strain becomes permanent, either ductilely or brittly. So each rock has some amount of elasticity with the stress that it's applied. And then at one point, or at the yield point, is where it no longer can accommodate that stress and will either bend or break. So when we're looking at rocks, we try to create a trained eye as geology students to see deformed strata and undeformed strata. So undeformed strata is generally something that is horizontal because rocks are laid down horizontally. There's no reason for them to, gravity doesn't say that it would just lay down like this, right? It's going to slide down into a valley and then stack up. So when we're looking at unstrained or undeformed strata, we're looking for something that has horizontal lines or horizontal beds. They have spherical sand grains, so nothing weird in the sand. There's no folds, there's no faults. Okay, but deformed strata would be something like these tilted beds where there's angles, so they're tilted, or maybe there's some metamorphic alteration, so you have that foliation fabric in the metamorphic rocks. Maybe you have folding, maybe you have faulting. So if you see folds, faults, tilted beds, or foliation, you know that these rocks have experienced some sort of stress resulting in strain, and so they're deformed. Some of this information will be plotted on geologic maps. We've talked about geologic maps already in this class, but just kind of bringing us back, these show us a lot of these formations. So not only do they plot rock formations in whatever location those rocks are, but they can also show us where the faults and the folds lie, where we have inclined strata or tilted layers, and then of course the rock type, that we've already discussed previously. So one last little bit before we go, on these geologic maps, we oftentimes see something called rock attitude, which is the strike and dip of a bed. So in geology, when we're looking at faults and folds and tilted beds, we want to know how inclined and what orientation those rocks are sitting. So we call that rock attitude. It has an attitude. It's bent or broken or tilted. And we can make some interpretations about what it looks like in the subsurface based on what we're seeing at the surface. And so we'll take what we call a strike and a dip. And there's special symbols that we put on maps that look like a T. And the dip is the short line, which is the incline of the bed. And then the strike is the long perpendicular line that's usually to the right. So if you were standing and the dip was facing you, the strike is to the right, and then you would put that compass direction on your map, and you would say, okay, so this is the direction of strike, and then this is the direction of dip, and what angle that dip is inclined at. So with that, some summary and final thoughts. Remember, there are 3 stress types: compression, tension, and shear. Those 3 stress types are going to be stressed throughout all of the next few lectures. So keep those in the back of your mind. And for your final thought-provoking question, why might some rocks bend underground but break near the surface? So think about that. We talked about what can cause different types of deformation, different types of strain. So ponder that question, write it down in your notes, and I will see you guys in the next video. Bye.